So if you remember, last day we just realized that the Hamiltonian only depends on the quadratic part of the Lagrangian, quadratic in velocities, minus the independent part. Okay, so this is a general result, starting from a Lagrangian, which is quadratic in velocities, with a kinetic energy, which is the usual 1/2 of mv squared. And now we're going to see, what is the relationship between the Lagrangian and the Hamiltonian in a generic case. Okay, so let's just start from a Lagrangian L, which is going to have a quadratic part, a linear part, and an independent part of q squared. And this is going to be 1/2 of q. I'm going to put all the q's into a vector, transpose. A is going to be a matrix, and q dot is going to be another vector. So this is the usual quadratic part. I just organize it as a row, an n by n matrix, and a column. Okay, and the linear part I can also write as a vector, transpose, times another vector. So I hope, so this is a row and this is a column. The row times a column is a number, which is what a Lagrangian is supposed to be. Okay, plus L0. And L0, it's just going to be a function, so it's not a vector or anything. So the matrix A is, of course, a function itself of all the generalized coordinates and time. And this vector A here is also a function of all the generalized coordinates and time. Remember that I have qi of t coordinates. I goes from 1 to n. Okay, so A is an n by n matrix. So the question is, once I'm given this Lagrangian, what is the form of the Hamiltonian? And now the whole thing is prepared so that the answer to this question is going to be very easy. I just have to construct the Hamiltonian from this Lagrangian, and there's going to be a connection between the form, acquired by the Hamiltonian and the form that I'm assuming for the Lagrangian. Before I do this, okay, so let's go back to make the following point. Okay, so the term q dot A is transposed because is a row, and q dot, which is a vector, this in components is nothing but the sum over I and j from 1 up to little n of aij q dot I q dot j. You guys agree with this? Simply, right? It's nothing else but this. Okay?
Yep.
All right. Now, the thing to notice now is that aij in this sum is actually symmetric. Necessarily has to be symmetric. Is that clear? Does anybody know why these coefficients aij necessarily have to be symmetric in this sum?
A matrix is a quadratic form, so we can always symmetrize quadratic form.
Yeah. But I mean, in principle, this matrix here could have, I mean, what is true is that any matrix, so let's open a little note. What is true is that any matrix Mij, I can always decompose. I mean, this is a general matrix, okay? Two indices, n by n matrix, if you wish. I can always decompose any matrix into a symmetric part and an anti-symmetric part of that matrix, because I can always write Mij plus Mji divided by 2 plus Mij minus Mji divided by 2. This is obviously true because the MJI and the MJI here, they cancel each other. And 1/2 and 1/2 gives me 1. So that is absolutely true. Now, this object here, the first term, is obviously symmetric ij. So Sij is the same as Sji. And this second term here is obviously antisymmetric. So Aij is minus Aji. And this is for any matrix M. So this is true. I can always decompose any matrix into a symmetric and an antisymmetric part. But why can I say that here it's only symmetric?
Because the subindex are dummy.
There should be a what?
Because the subindex are moods, or dummies. No sé cómo deies.
Yeah. They are dummies. And so yes. So what? I mean, the fact that these are dummy indices.
Well, you can change them, and then they will be symmetrical. I mean, they can you can change J for I, and you will have like the opposite part of the matrix.
It's almost the right answer. So what is? Yeah, why don't you think just 1 second more, and you tell me why these coefficients here necessarily have to be symmetric? I mean, if the matrix Aij is not symmetric, imagine that I have an M here, a general 1. I can still decompose this thing. And so I'm saying that only this part is the one that, remains in here. Why?
Because they are the same vector.
No, the answer is because the antisymmetric part gives you 0. If you have sum over I and j, Aij, Q dot I, Q dot j, in general, I can even write here any symmetric part, Sji. This is identically 0 if S is symmetric and A is antisymmetric in the exchange of indices I and j. So proof of that, and it's based on what you said. It's based on the fact that the indices are dummy. Okay. So let's just change I and j in A. So if I change I and j, I'm changing the sign. Agreed?
Yes.
And I can also change I and j here, but here I don't change the sign because this thing is symmetric. Right? Right.
Yes.
Okay. So this is minus the sum over, and now I'm going to call J, I'm going to call it K. And I'm going to call it L. Okay? And after I do this, I don't like K and L. That's a minus. I like to call K J because I like it better. And I don't want to call it L. I want to call it I. And because they are dummy indices, I can do that freely. And what do I find? I'm sorry, I wanted to call Ki. So I made a little mistake here. So let's go back. Let's go back. To make the point, I think it's better that I do it like this. I want to call K, I want to call it I. So that's going to be sum over I, and here I have an I, and here I have an I. And now L, I want to call it J. J and J. Yeah, now, and what do I find? What I find is that this thing equals minus itself. So that means that is 0. And I close the note. Okay?
Yes.
Okay. And I didn't cheat, huh? So this is not a mistake I didn't do anything illegal. Everything that I did was fully legal. I'm just, renaming indices. And this I can always do, whenever the indices are dummy, as this one, okay? So this is perfectly fine. And this is telling me that whenever I contract, this is a contraction, right? This is a contraction. Whenever I contract a symmetric matrix with an antisymmetric matrix, the answer is 0. And this contraction is the same as the trace of the product. If you look at the indices, how they are organized, and I'm summing over all of them, so that goes all the way up to n, then this is nothing but the trace of A times S, right? So you see that the index J is correctly multiplied. So the lesson that we learn is that in here, these coefficients, maybe they could have an antisymmetric part, but that antisymmetric part will not contribute to the sum. So therefore, in the sum, it's only the symmetric part that contributes. So I can take these coefficients here symmetric. Actually, I'm going to change them. I'm going to call them little a, so that you guys don't get confused. So this is going to be A, this is going to be Aij, this is going to be Aji. So let me just write this thing clearly like this, okay? So this is little a, so that you guys don't get confused with this capital A, which means an antisymmetric matrix. So this is just, this is a side remark, okay? All right, so that means that these coefficients here, I can take them to be symmetric. And this is going to be helpful because now remember that the Lagrangian was 1/2 of, the sum over I and j from 1 up to n of Aij q dot I q dot j plus q dot I AI sum over I from 1 up to n plus L0. So that I've written again the expression for the Lagrangian, not without vectors, but now, using sums. And now I have to define my canonical momentum, right? So the canonical momentum pk is going to be the derivative of L with respect to q dot k, right? That's what I have to do. And so this is what I have to take the derivative of the above expression, this expression here, with respect to q dot k. So that means that I'm going to get a 1/2, a sum over I and j from 1 up to n, Aij, derivative with respect to q dot k of this product, q dot I, q dot j, plus the derivative of the sum from I equals 1 up to n, a sub I, derivative of q dot I with respect to q dot k, right, plus 0, because L0, by hypothesis, does not depend on q dots. Agreed?
Yes.
Yes.
Okay, so let's start with this one. What is the derivative of q dot I with respect to q dot j?
Kronecker delta.
Yes, delta ik, that's right. And this one here, this is going to be the derivative of the first one, which is delta ik q dot j plus q dot I delta jk, right? Okay, so this means that pk is going to be 1/2 of the sum over I and j from 1 up to n of Aij times this one here. So let me just, just do the sum. Let's do the two terms. So the first term is Aij delta ik. So that means A kj q dot j, right? Because the delta kills all the contributions if I is not k. So that means that, I is exactly k. to be non-zero. Plus, and here, the same story, but now for j. So delta jk aij, that means it's aik q dot I, plus this sum here, which kills the whole contribution unless I equals k. So this is ak. All right. Now, because these objects here, and here I have to be a little bit more careful. I have to separate this sum. Huh? So I have to put here, this is going to be the sum over j from 1 to n. And that is because, I has been, already frozen to be k. And these other ones, I also have to change sum. So this is just sum over I from 1 to n. Okay? Now, in this second sum here, let us look at this second sum. The I index is against, a dummy index. So that means that I can change I, and replace it for any letter I want. So I'm gonna write here J. So the I is gonna become J. So I put a J, J, and J. Okay? And so therefore I find 1/2 of the sum over J from 1 to n of AKJ plus AJK. Now I can put the two terms together, times Q dot J plus AK. But remember that these guys were symmetric. So that's why I had to make this point at the beginning. They are symmetric. So therefore, they are twice one of them. And now, finally, I can rewrite this thing as PK equals 1/2 and the 2, cancel out. And then I have a sum over J from 1 up to n of AJK Q dot J. Well, actually, I can also write it in the other way, because since it's symmetric, I can also interchange them, and it's going to look a little nicer. So AKJ Q dot J plus AK. And so what this equation says in components is that P vector equals the matrix A, whose components are AKJ, times Q dot vector plus vector A. Okay, so let me I'm going to write it again. I'm going to write it again here so that I can frame it. I can put it in a frame. Okay, so P equals A Q dot plus little a. And this is important. So I frame it. Okay?
Okay.
Good. Now that I know this thing, now that I know that P equals A Q dot plus little a, this means that Q dot equals, well, nothing but A minus 1 acting on P minus A. And this is what I need in order to construct the Hamiltonian, right? Because remember, the Hamiltonian is, Q dot P minus the Lagrangian, right? Which usually we write as Q dot I Pi minus L, but that's what it is. Okay, so this is what now? So Q and P, that means that I have, so let me write it the other way. For instance, it's going to look a little nicer. P transpose times this. So that is then P transpose times A minus 1 times P minus A minus the Lagrangian, which is 1/2 of what? 1/2 of, remember that L is 1/2 of Q transpose A Q dot plus Q dot transpose times A plus L0, right? So that's minus 1/2 of Q dot transpose, and this I have to write here. Again, the transpose of this object, so that means P minus A transpose A minus 1 transpose times A times Q dot, which is A minus 1 times P minus A, plus A times Q dot transpose, which is the transpose of this thing. Oh, let me write it. Q transpose, which is P minus A transpose A minus 1 transpose A plus L0. So all in all, you compute all these things and you organize the calculation, and what you find is that this is nothing but 1/2 of P minus A transpose A minus 1 times A minus 1. So I'm going to give you the answer already. So you work it out. So this is going to be A minus 1, P minus A minus L0. So that's what is left. Okay. So the Hamiltonian for a Lagrangian of this form looks like this. Any questions about these manipulations? They are very simple. You just have to work it out, step by step, and that's it. I don't think that there's going to be any difficulty, but just in case you guys have any question, you have any question?
No.
Okay. All right. So notice that the same matrix which is sitting here inverse. And this little a here is also, in this term here, subtracting, okay? And remember that we also found that P is A Q dot plus little a, this little a here and little a here. So this is an example. So notice this thing. This is important. Notice that this is an example in which P is not proportional to Q dot. It has an extra term. And this in general may happen. Most of the time what you find is that P is proportional to Q dot and that's it. But in general, it could happen, and we'll see an example of a physics system in which it does happen. There is an extra term. Okay? So let's see a couple of examples, so that you see that it actually happens what we're saying here in general, okay? So again, this is the motion. So that's example number 1, is the motion of a particle of mass m in a central potential. Okay, so we already know that the Lagrangian is 1/2 of m r dot square plus r squared theta dot square plus r squared sine theta square phi dot square minus the potential, okay, in a spherical coordinates. We already saw this the other day, okay? So this means that I can identify my matrix A as m times 1 r squared and r squared sine theta square with zeros in the off diagonal, okay? And the vector A is actually 0. There is no linear term in velocities. All the velocities appear in a quadratic form, okay? And L0 is minus V of r. So given this, we can immediately write down the Hamiltonian. The Hamiltonian is going to be 1/2m by the way, here I forgot an M. Here I forgot. Oh, no. Here is okay if I absorb the M in what I define to be the matrix A. So this is going to be 1 over 2M times PR, P theta, P phi. Here is the inverse of this matrix. So this is 1 over R squared and 1 over R squared sine squared theta with zeros in the off diagonal. PR, P theta, P phi, plus V of R. Okay? So, and that's exactly the Hamiltonian that we found the other day for exactly this system, a particle of mass M in a central potential. So it's an example of how, you know, these things actually connect to each other, as we saw. So that's one example. That's a simple one. Let us look at another example in which there is a linear term in velocities, okay? So that's example number 2. And this is going to be a particle of mass M, again, in an electromagnetic field. All right? So the kinetic, so far we're always treating all these particles non-relativistically. So that's the kinetic energy. And now the potential. What is the potential of a particle in an electromagnetic field? Who can tell me what the potential is? So an electromagnetic field is characterized by a Coulomb part and a vector potential A, right? That's one way to characterize an electromagnetic field. Alternatively, I could also talk about the electric field and the magnetic field, but I'm going to give you a hint that these are the variables that we're going to need to write down the potential. Does anybody know what the potential is for a particle of mass M? Ah, and I forgot something else, and charge, electric charge Q. In an electromagnetic field, what is the potential for that? Huh? What's the potential energy? If I have a Coulomb potential and a charge Q, what's the energy for that system?
Q times phi.
Yes, so that's there. Yes. But now the particle is moving with a velocity v. Okay? And we know that if you have a particle with charge q moving in a velocity with a velocity v, and you have an electromagnetic field, there's going to be a magnetic field b, and there's going to be a force, right? Because a charged particle moving in a magnetic field b, you know, feels a force, the Lorentz force, or whatever you call it, a force. Okay, so what is the potential energy in that case? And I'm giving you a hint. Huh? It has to be written in terms of the vector potential A, not the magnetic field B. Who knows this?
Minus Q
Yes?
and the dot product between the velocity and A.
Yes, very good. So yes, absolutely. This is the answer. So this is now the potential energy for a particle of charge Q moving in an electromagnetic field whose Coulomb component is phi and whose vector potential is A. So, okay, so now we have the Lagrangian. It's 1/2 mv squared minus u, so that's minus q times phi minus b dot A. Okay? Now, given this, you immediately realize that the canonical momentum P is going to be now mv, but there is an extra piece, QA, right? That was the little a we had before. So now it's not just mv, huh? P is not just mv, has an extra piece. And this is the real canonical momentum, okay? So it's not the, what we could call this thing the kinetic momentum or the linear momentum, but it's not the canonical momentum. So for instance, if we were to quantize this theory, this capital P would be the one that would have, a commutator with the position to be IH bar, okay? This is the guy that has to be quantized, not this M times B, okay? All right, so given this, now we can construct easily the Hamiltonian, right? Because that means that our matrix A, referring to the previous case, right, is M times the identity matrix, if you wish, right? And this little A vector is Q times the vector potential, and L0 is minus Q phi. So I'm just identifying, the different terms that we had in the previous case. So that means that the Hamiltonian can be written already straightforwardly. Then this is 1 over 2m times P, the canonical conjugate momentum, canonical conjugate momentum, minus QA. So that's the shift, this little shift here with the opposite sign, transpose. And this is the unit matrix, because this is going to happen for each component of this vector, times P minus QA and plus Q phi, plus Q phi minus L0. Okay, so this is the same as 1 over 2m P minus QA whole thing squared plus Q phi. This is the Hamiltonian. So first thing that we see here is that because of this, because the Lagrangian has this extra term linear in the velocity, the canonical conjugate momentum is not the same as the linear momentum. It's not m times the velocity. So that's the first thing. Second thing that we see is that the Hamiltonian is not the energy of the system, because the energy of the system, by definition, is the kinetic energy plus the potential. And this is 1/2 of mv squared, right, plus q phi minus q v dot a, right? That's what it is. That's the energy. And this has nothing to do with that, because remember that this object here is similar to that, but this other term is not there, okay? So it is different, okay? If I call this thing little p squared, so little p is nothing. It's just a definition of m times v. This little p is no longer the canonical momentum. The energy is p squared over 2m plus q phi minus little p divided by m times a. And this is not this. It's a different object. Okay? I mean, in particular, there's this linear term here, and here there isn't. Okay? So here the Hamiltonian is not the energy. And so now there is a question, so when is the Hamiltonian the energy? And this is a question that we'll try to answer next. But there is something else that is worth noticing in this particular case. And this has nothing to do with the construction of the Hamiltonian. It is actually more profound than this, which is, look at this Hamiltonian. So let's, oops, I wanted to do it in red. See if I can do it in red. Man, where is my red color? Ah, here. Here is my red color. Right? Notice the following. We found that H equals 1 over 2m P minus QA squared plus Q phi. So I'm going to take the Q phi and I'm going to pull it to the left-hand side. H minus Q phi equals 1 over 2m P minus QA squared. And now let us compare this with the Hamiltonian that I would have in the limit in which the electric charge would be 0. So if I set Q to 0, I would find H equals 1 over 2m P squared. Obviously, because if I set the electric charge to 0, then the system becomes free. There is no interaction with any field anymore, because without a charge, there is no electromagnetic interaction. But now I can read this thing backwards, right? And I can say that a free system becomes interactive, so that's the interaction, by replacing P goes to P minus QA and H goes to H minus Q phi. This simple replacement generates from a free system the electromagnetic interaction. This is trivially true, and it sounds something very simple, very naive, very trivial, but actually is extremely important. And this is why I want to mention it at this point. Is this replacement here is called the gauge principle. The gauge principle. It tells you that in order to find, how a particle interacts with the electromagnetic field, all you have to do is write down the Hamiltonian for that particle as if it was free, and then make this replacement. Okay? And one would say, well, maybe this is just a coincidence of the electromagnetic interaction. Maybe the electromagnetic interactions are such in which this thing happens to be true. Well, look, it could be something else, but it is this. Well, actually, this is not the case. This is the way all fundamental interactions are generated in nature. And this is a principle now, okay? It so happens that this is the case. All interactions, gravity, the electric and magnetic, so the electromagnetic interactions, the weak interactions, and the strong interactions, those are the 4 interactions that we have in nature. They all obey this gauge principle. So they all obey the fact that to generate the interactions, you just write down the Hamiltonian for the free system, and then you make this replacement. We will soon see that this replacement is actually, relativistically covariant. So this is something that we can also do in relativistic theory. So it is really profound. It is telling you, how and why the interactions are the way they are. Okay, it doesn't seem to be a coincidence. There is this underlying principle governing, the generation of all the fundamental interactions in nature. Anyway, so this is just a side note that, I couldn't resist but doing here. Let's go back to the question that we also had to answer, which is, when is the Hamiltonian the energy? Okay. So conditions for H equals E. Okay? So because now we are in a good position to answer this question. So who is H? We just saw that H is L2 minus L0. There is no L1, right? H only knows about the quadratic part and the independent part of Q dot, which means that it is T2, so the quadratic part of the kinetic energy, minus V2, the quadratic part of the potential, if there is a quadratic part in velocities in the potential, minus T0 plus V0, right? That's what it is, because L2 obviously is T2 minus V2, and L0 is T0 minus V0. Good. So that's what we have on one side. On the other side, what we have is the energy. But the energy is the total kinetic energy plus the total potential. So that is T2 plus T1 plus T0, if there is a T1, is the total kinetic energy. So therefore everything, the three terms. Plus, same thing for the potential. And now the question is, when is the Hamiltonian the same as the energy? And what we immediately see is that for this thing to be true, first thing that has to happen is that T0 has to be 0. Let's just start with this guy. Okay, so here I have minus T0, here I have plus T0. So that means that in order for these two things to be the same to begin with, this term has to vanish. So there cannot be a T0. But what was a T0? Remember, let's go back a couple of pages. Where is my T0? Here, T0. T0 happens to be a sum over the masses of the derivative of the position vectors with respect to time, explicitly a square. Okay? So the only way this term can be 0 is if all the positions here do not explicitly depend on time. So this dependence in T cannot be there. Okay, so let's go back. All right, and this means that the derivative of r with respect to t explicitly has to be 0. Or, in other words, Ri is Ri of all the q's, but there can be no time dependence. Okay, so in other words, the constraints have to be time independent. There cannot be explicit time dependence in the constraints. Okay? Okay, so that kills the T0. Okay, fine. T0 is not there. But we still have to satisfy more conditions, right? Because here there is no T1, and here there is a T1 and a V1. So T1 plus V1 also has to be 0. So that this T1 plus V1, which is not there, can make these two things agree, right? Now, once R does not depend on time, T1 is also 0. Because T1, you go back, 3 slides as we did. Well, let's do it. Let's go back 3 slides. Or 4 slides, or 5. Here. Who is T1? This guy is T1. So this guy is T1, okay? But T1 also has the explicit time derivative here. And we just said that this is 0 for the first condition, right? We also required that this thing, this time dependence did not happen. So that means that T1 is already 0. Okay, so then that means that V1 has to be 0. Okay, so that means that the potential may depend on R, but it cannot depend on velocities. right? The potential cannot depend on velocities. And this is the reason why the energy in the Hamiltonian is not the same for the electromagnetic system, because the potential does depend on velocities. Okay? Now, when the position vectors don't depend on time and the potential does not depend on velocities, then we have T0 is 0, T1, B1, T1 is 0 and B1 is 0, both of them. So that means that I don't have this guy and I don't have this guy, okay? But I still have to worry about T2 plus V2 versus T2 minus V2. So there is a third condition that I have to satisfy. Now, when the potential does not depend on velocities, and therefore V1 is killed, actually V2 is also killed. Because if it does not depend on velocities, it doesn't have a linear term or a quadratic term. It doesn't have any term in velocities at all. Okay? So then V2 is 0. Okay? So I need this condition, and then V2 is 0 also. All right? And then, so if V2 is 0, this guy here is also 0. It's not there. And then at this point, we have that the Hamiltonian equals T2 plus V0, and the energy equals T2 plus V0. So then, in this case, they are the same. If the position vectors don't depend explicitly on time, and the potential does not depend on velocities, the Hamiltonian and the energy are the same. Okay? So that's one result. Good. But we can say something else. We can also say, be a little bit more precise. Since now, Ri, let me just put it like this. Ri only depends on the Qs, but not on time, explicitly. If the potential, which cannot depend on velocities already, but in principle it can depend on the position and on time. If the potential does not depend on time, then what I find is that there is no time dependence anywhere, right? Because here there is no time dependence, because this guy here comes from derivatives of this thing. There is no time dependence anywhere, and therefore not only the energy and the Hamiltonian are the same, but they are also constant. Okay? So this is another result. Which is very useful and we will have to remember, okay? So if in all these conditions, when the Hamiltonian and the energy are the same, the potential does not depend on time, explicitly on time, then not only is the energy the Hamiltonian, but they are also constants of motion. Okay? Any questions?
No.
No questions? Questions or comments?
Well, Santi,
Yes.
if anybody has a question about this last class, I would like to ask you a question about previous slides.
Okay.
It is in slide 11.
All right, let me try to find it. Okay, so this is this slide 11, the one you're thinking of?
Yes. this one.
Okay.
On the top of it, I see that you substitute eta I for virtual displacement of Q. You
Yes.
said that they are equal, but in previous slides, we have the relationship between these two variables and they are not actually equal. So I am quite lost.
Yeah, I asked about this like some days ago. I don't
Okay,
know.
so maybe what you're saying is, let's see if you would agree with this. Are you happy now?
Yes. Yeah, I think that now, yes.
Okay, fine. So this was a little mistake. Fine, but there is, it doesn't have any consequence, right? It's trivially true.
But I mean, what you have instead of delta qi, you would have only eta I think. Okay, because
I don't know what you mean.
I will think more about it because now with the change I don't.
No, but I mean, the only thing is that here I was computing the derivative, right? On the left-hand side, derivative of s respect to alpha. And here, instead of writing the derivative of dq respect to alpha, and then it would be exactly right, I just wrote the differential. So I forgot to write the d alpha. Now I'm writing the delta alpha. Fine, but it's the same. I don't see the difficulty, frankly. What?
Okay, but now when you have only delta qi, you say that the lemma says that all the thing within the integral is 0.
Yes.
And I think I remember that the lemma said that you had to have a function multiplying the integrand to say that the integral was 0.
No, but look, so let me just write here a little note. Note, if you have integral dt of m of x times eta of t, I'm sorry. Times eta of t equals 0 from t1 to t2 for all eta of t, okay? That this leads to m of t equals 0. What's the difference between saying this thing or saying m of t, eta of t equals 0 for all eta of t? It's exactly the same.
Yeah, okay. Okay, yeah, sorry. Okay.
Right? It's exactly the same. In the previous equation, what I had before, I forgot the delta alpha. Fine. So now I put the delta alpha. So, but the statement is exactly the same. There is no difference whatsoever, as far as I can see. I mean, I don't know. I don't really understand what is the, the difficulty that you guys have. Okay, so bye.
Okay, bye.
Bye.
Bye. Bye. Yeah.